The new year 2021, and I hope it brings you a lot of joy and happiness. We had an amazing start in 2020 and we talked about magnetism, we have talked about magnetic effects, we have talked about magnetic field due to current carrying wires. And today we are going to dwell more and we are going to figure out why exactly magnets behave the way they behave and what is exactly there inside a horseshoe magnet, inside a bar magnet and stuff like that. So we are going to go at atomic level and then we are going to see some amazing formulas for bar magnets, which is there as your very important portion. It's a very important portion for JEE Mains as well as advanced and other competitive exams like KVPY, NEET, BITSAT, CET and you name it. So welcome everyone, this is Shreyas here, your master teacher for physics and your anchor for this channel, we Enthuse. So welcome and a very happy new year. I hope this year is really different. I mean it literally, and I really hope that the vaccine comes and we all are going to be really safe from this virus out there. So welcome, hello Kevin, hello Tanmay, hello Yalini, hello Kirito, hello Ankit, hello VK channel, hello everyone, hello Dinesh, Anish, Sankar, Elakia and Krito, welcome everyone. So let me know guys, what is your new year resolution, and I'll tell you mine very soon on Instagram, and you can follow me on my Instagram account, that is Shreyas_Vedantu, to know what is my new year resolution. So those of you who do not know me, this is Shreyas here and I have been teaching for almost a decade and many of my students have qualified the IIT examination, KVPY examination and all the other entrance examinations which are required for getting you into an engineering college. And many of my students have also scored 2-digit All India ranks, and I myself have cleared IIT back in 2005. So having said that, I really love physics and I really love teaching, so that's why I'm here. So welcome to this very special channel, We Enthuse, which is your one-stop destination for the engineering entrance examinations. Hello Sneha, hello Mohit, hello Bijin, hello everyone. And you can also greet each other, you can welcome each other, make new friends out here in the chat box. Remember, the only way you can mark your attendance is by saying hello and saying a few words to your fellow minions out there. And before I forget, do not forget to hit the subscribe button down there, because if you do not hit the subscribe button, how else are you going to get all the new videos, amazing updates and all the amazing quizzes, mentees and so many other things that we have planned for you. So do not forget to hit the subscribe button down there, and also if you have hit the subscribe button, do not forget to hit the like button out there, because unless and until you smash that like button, we are not going to get the energy to conduct today's session and YouTube is not going to recommend our videos to you. So go ahead, smash that like button out there. Hello everyone, and I hope you guys are doing great. Yes, Sanish is asking Kirito to increase his level of jokes this year. That's interesting, but Kirito has been cracking really good jokes, and a lot of other people also, I remember, have a really good sense of humor out there in the chat box. So keep the jokes coming guys. And hello Pratiksha, hello Dinesh, hello, hi, I'm not sure what the name is. Okay, hello, welcome. Oh Shankar, no problems, you can start preparation for JEE no matter when guys. And I hope guys you know what is special about today's session. It's a marathon session, yes. So get your drinks ready, get your sandwiches ready, and please also keep your notes out, because you have to make a lot of notes, you have to solve a lot of problems. It's a marathon session on magnetism. We are going to talk about how magnetism comes into play, how bar magnets can attract or repel each other, what exactly happens at the atomic level, and also the magnetic properties, and we are going to also talk about bar magnets as well. So welcome everyone. Hello Aishwarya, hello Sana. Welcome everyone. And remember, tomorrow is a chemistry Menti quiz at 9 o'clock, so do not forget that. Alright, so Sunday chemistry Menti quiz, and in case you have missed any of these classes out here, so please go ahead and check it out. is there in our playlist. So do not forget to check out all the videos, because only then you can stay up to date. So let's begin our amazing class today, and I hope the Josh is really high, and let me know if your Josh is really high in the chat box down there. So let's begin. So remember, we have spoken about magnetic field, we have talked about, you know, even how currents can produce magnetic field and stuff like that. So we know that a bar magnet produces magnetic field around it, something like this. The field lines roughly try to originate from the north side and they appear to terminate on the south side, but actually speaking they continue inside the bar magnet as well, from the south to the north. Remember, that's a very important property of magnetic field, that it never starts or ends actually, because it is always in the form of closed loops. The same way for a horseshoe magnet, the magnetic field lines look roughly like this, and you can very easily see how the magnetic field lines look like by taking any kind of magnet and taking a piece of paper and sprinkling some iron fillings over there. Tap that paper, let the iron fillings settle down, arrange themselves in the direction of the field, and you will see roughly this is the direction, or this is how the magnetic field lines are going to look like for a horseshoe magnet. They will originate from the north pole, terminate at the south pole. You can see it's very strong near the poles, and it becomes really weak as you go really far away from the poles out there. Okay, so Ankit has come prepared with fruits. So Shreya, the KVPY session is going to be on Monday. So by the way, those of you who are very new out here, so guys, I have planned a very special KVPY session again on Monday. There are in fact 2 KVPY sessions next week. The timetable will be out very soon. Do not forget to check out the Telegram group down there. Join it, because all the important updates, the notifications, the timetable for the next week will be updated on the Telegram channel. So do not forget to check out our Telegram channel as well. I have planned 2 KVPY sessions and SHM continued next week, along with electromagnetic induction and Menti quizzes, of course. So okay, so let's get going then. Let's get going. So Shankar, maybe you can also put up comments after the session is over, you know, below, and I will be more than happy to help you out with any doubts that you have, or you can even contact me on my Instagram account, Shreyas_Vedant. All right, and others are also there who can help you out. Thank you, Pratiksha, so much. And all right, and Sneha has come with papads out there. Very good, very good. Kya baat hai? All right, papads. It's nice, interesting. Which kind of papads? I love all kinds of papads, by the way. Okay, so here's your first question for today. What are the direction of forces on the poles of a magnet placed in an external magnetic field B0? This is a magnet, guys. Think about it. What will be the direction of forces on the south pole and north pole? Come on, quickly let me know the answers in the chat box. All right, Ankit already has said C. Okay, Kirito also says C. Come on, guys, come on. What do you guys say? Dinesh says C. Aishwarya says D. All right. Come on, everyone. Sneha also says C. Okay, Princey says C. Everyone, come on. What do you guys say? Is it C, D, A, or B? Come on. Think about it. What will be the direction of the forces on it? All right. Realni says C. VK channel says D. All right. So here is the correct answer, guys. The correct answer is actually C. Now I'll be like, how the hell is it C? See, it's very simple, guys. Field and force are always along the same direction, provided the the charge or the pole is also positive. Now, north pole is always positive, south pole is always negative. Just like if you take a charge and if there is electric field, the force on the charge is in the direction of the electric field, right? Provided it's a positive charge. If it's a negative charge, the force is in the opposite direction. Same way, on the north pole, what will happen? The force will be in the direction of the field, and on the south pole, the force will be in the opposite direction of the field. So on the north, it's towards the right, and on the south, it's towards the left. Hence, the correct answer is option C. I hope I made sense and you have understood this answer. All right. Very good, Ankit. Keep it up. And others as well who have given the right answer. And do not worry if you have not given the right answer, guys, because remember, you have come here to learn. It is obvious that you will not get everything correct, and nobody is going to judge you here. And be confident, it's okay. Even if all the answers are wrong, we still love each other and we are still going to support each other. So do not worry, be confident, post all your answers down there. Okay, now this is what we are going to talk about. What happens when you take an object, okay, and place it in somebody else's external magnetic field, guys? So what is exactly going to happen to that object? Remember, in electrostatics, I have told you that if you take a material and place it in somebody else's electric field, remember, polarization happens, induced electric field is there, and because of that the field inside that material is weakened by K times. Remember all that? Similar things are going to happen over here. Yes, when you place an object in external magnetic field, you will see there will be an induced magnetic field, and that magnetic field can be opposite to the external field, or it can also happen that if this is the direction, B0 is the external field, the induced magnetic field can also be in the same direction. Both possibilities are there. Remember, in electrostatics that was not the case, it used to be always opposite, but in magnetism both possibilities are there, and that's why things become little bit interesting, and that's what we are going to see. Now first, write all these things down as I write. So what is this B0? This B0 is nothing but your external magnetic field. So this is your external magnetic field. Then what is this B induced? This is nothing but the induced magnetic field. All right, this is your induced magnetic field because of the atoms, because of the molecules, because of the structure, the way it is. It can be in this direction or it can be in this direction, depends, guys. And then I'll have one more term called as B, just B without any subscripts. This is the net magnetic field, very important, net magnetic field. And this net magnetic field is the vector sum of the external field plus the induced field. Understand, I have put a bar symbol, so the magnitude can be either addition or subtraction of these two quantities. If both are in the same direction, magnitude wise it will be B0 plus B induced. If induced and external are in the opposite direction, then magnitude wise it will be B0 minus B induced. Has everybody understood this? Let me know. Let me know if you guys have understood this and you have also made notes about this. Okay? So very important, this is the net magnetic field inside the material, which will be the vector sum of the external as well as the induced magnetic field. And guys, if you have not liked the video yet, please go ahead and like this video, guys, because I'm doing all this for free. So at the least thing that you can do out there is at least go and hit the like button down there. All right, very good, perfecto, excelente. Let's get going. Now there are some crazy terms out there which people get confused. Magnetic intensity, intensity of magnetization, permeability, relative permeability, susceptibility, this, that, and how these are related and their problems, and diamagnetism, paramagnetism. Guys, hold on, I'm going to tell you all about this and you will never forget all these terms after today's class. So get ready, start making notes. Here's the first term coming up on your screen, and that is called as magnetic intensity or magnetizing field. Both of them mean the same thing, magnetic intensity or magnetizing field. Now I'll give you an example. Imagine there is some material, it could be any material. Let's say this is the material. I want to magnetize it. So I place it inside some solenoid or bring it in front of some other magnet. So how strong is that external field is given by this particular term out there, which is called as magnetic intensity or magnetizing field. How strong that external field is, that is called as magnetizing field. And that value, guys, that value is given by, or first let me tell you the symbol. The symbol is H. H is the symbol for magnetizing field, and that is nothing but B0 by mu naught. Remember what B0 was? We are going to stick with the same symbols. It's the external field. What is mu naught? It's the permeability. It's just the permeability of free space. So that is the formula, guys, for H. Okay, so very, very important terms. This is your external field which is trying to magnetize a material, and this mu naught is nothing but just the permeability of free space. This is the permeability of free space, nothing more, nothing less. And we all know mu naught by 4 pi is nothing but 10 to the power minus 7. So mu naught by 4 pi is nothing but 10 to the power minus 7 SI units. Very, very important. Now let's take an example. Say for example, I place some material inside a solenoid. So due to a solenoid, what is the value of H? The value of H will be B naught by mu naught. But if you recollect the formula for magnetic field due to a long solenoid, try to recollect guys, the formula was mu naught Ni, where N is the number of turns per unit length, I is the current flowing through it, and mu naught is there downstairs. These both values get cancelled and you will just have Ni. So H is Ni for a solenoid, remember. Is that clear? Very, very important. Very, very important. Yes. So this is called magnetic intensity or magnetizing field. Very, very important. I hope you have made notes about it. Excelente. Very good, Mr. Best. I really hope you really are best. And yes, Ankit, I will tell you about my New Year's resolution on Instagram, alright? So follow me over there to get to know more about it. Now, the next term, guys, come on, get ready for the next term. The next term is intensity of magnetization or just magnetization. The symbol for that is I. Now, see, a solenoid produces magnetic field. It has its own magnetizing field H. How much does the material get magnetized? So you can place a wood, you can place some water, you can place iron, you can place aluminum. Each material will respond differently. So what is the intensity by which it got magnetized? That is called as intensity of magnetization. So how well did it respond to it? So that is nothing but, any guesses guys? So that is nothing but B induced by mu naught. How much magnetic field was induced in it divided by the permeability of free space? That is nothing but I. And I hope you are seeing that the unit for I as well as H is the same. Yes, I did not tell you the unit there, but understand in previous formula it was B naught by mu naught. Here it is B induced by mu naught. So the formula is the same. I hope this is very clear. And remember, we just saw that for a solenoid it was N into I. H was Ni. And remember, the unit of H and the unit of I is the same. And what should it be? Think about it. N into I, number of turns per unit length. That means number of turns does not have any unit, so it is per meter, and current is nothing but ampere. So the unit will be nothing but ampere per meter. So this is the unit, guys. This is a unit for H, I, both of them are same. Yes, very, very important. Okay, now if this has been registered in your head, let's also talk about another formula for I. So guys, remember I have spoken about magnetic dipole moment. The symbol was capital M. So if this material which has been placed inside the solenoid gets magnetized, it will have some north pole and south pole. Correct? It has got magnetized. So it will also have some magnetic dipole moment. So this is the magnetic dipole moment. Correct? So this is the magnetic dipole moment due to the external field, in this case provided by the solenoid. This I can also be written down as the magnetic dipole moment divided by volume. So this is the alternative formula for I. So either ways you can get the answer. Remember that. Okay. So remember all these formulas. Very, very important. Very, very important. Okay. So magnetic dipole moment per unit volume of that object is called as how intense is that magnetization. Now, lot of people get confused between these two terms, H and I. So how do you remember it? Very simple. Intensity of magnetization, which is the first alphabet, I. So that's the formula, guys, I. So the first letter, that's what you need to check. So intensity of magnetization, symbol is I, and that is how much did it get magnetized. So it will be induced by mu naught. Magnetic intensity, the first letter is M, so it's not I. So the symbol is H. That's how you remember it. It's not I. So H is nothing but B naught by mu naught. Very, very simple. All right. All right. Very good. Hello, Khushbu. Join in, join in, join in, join in. Hi, Mohammad. All right. All right. Epic. Chalo. Let's get going to the next term, which is called as susceptibility. Now, an external field B naught will magnetize that material and there will be some induced field. How susceptible is that particular material? How susceptible is that particular material is given by this susceptibility. So basically it's nothing but, understand, what is the ease of getting magnetized. So this is nothing but the ease of getting magnetized, okay, and this X, it looks like X but it's a Greek X. This is how much did it get magnetized upon how much did you give. Remember, this H is your input. Remember, it was provided by the external field. This I is like your output. How much did it get magnetized? So X is nothing but I by H. So if I talk about the unit, please understand H and I both have the same unit. So it is a dimensionless entity. So X or susceptibility is a dimensionless entity. Very, very important. Very good, Yalini, Yalika. Very good, very good. Now, if this much is clear, let's go ahead to the next pointer, guys. Get ready for the next pointer. So you can just call it as susceptibility and just write it as X, because nobody is going to ask you pronunciation, Dinesh, but you can also check out on Google the exact pronunciation and all that. All right. So let's get going then. Next is permeability. Okay. So next up is permeability, guys. So what is permeability? So permeability is nothing but, so it tells you how permeable is a material. Matlab how many or how do the lines of magnetic field, how can they easily penetrate a material? So that is given by permeability. Very, very important. So basically understand, it's nothing but the degree of, so it's nothing but the degree of, how penetration, you can say. So it's nothing but the degree of penetration of the field, and that mu, okay, permeability. So remember, X was I by H. Here mu is not I by H, guys, it is B by H. Always H is in the denominator. That's all you need to remember. So mu is nothing but B divided by H. Very, very important, but this is not dimensionless. Be careful. B and H do not have the same dimensions. Okay. Now, if suppose, okay, if I talk about what is the permeability of free space. So for free space, what is the permeability? The answer for that will be just mu naught, correct? The permeability of free space, I just told you, it is called as, it has been defined as mu naught. Now relative to free space, how permeable is this particular material? That is called as relative permeability. So relative permeability is nothing but how much is the permeability of a material divided by permeability of free space, and the symbol for that is mu r. So mu r is the symbol, and this is something like your dielectric constant, which is the ratio of epsilon and epsilon naught, something like that. This is relative permeability. Very, very important. So permittivity is different. Permittivity is for field. Permeability is for magnetic field. Permittivity is for electric field. Permeability is for magnetic field. Remember that. Dielectric constant is for electric field. Relative permeability is for magnetic field. I hope this is clear. I hope this is clear. Okay, very, very important. So what is the degree of penetration of the field is given by permeability? It is B by H, and for free space it is mu naught. So their ratio, this is going to be dimensionless. Remember that. So it is dimensionless quantity because it's just a ratio. Very, very important. I hope you have made all these notes. Very, very important. Porosity and all that is not there, Khushbu, don't worry. That's not there. Okay. So now, what is the exact relationship between all these variables? That's what we are going to talk about. Remember, just some time back, I told you that the net field is nothing but external field plus the induced field. Didn't I just tell you about it? And I also told you that, H is nothing but B naught by mu naught. And I also told you I is nothing but B induced by mu naught. So I feel that we can somehow take these things over here and substitute. And how will it look like then? Therefore, B will be equal to, think about it, B naught will be H mu naught. So this will be H mu naught plus B induced will be I mu naught. Correct? So this will be I mu naught. Now let me take H mu naught as common, and I'll be left with 1 plus I by H mu naught. I have done this deliberately because I know I by H is a very special number. So what is I by H, guys? I by H is nothing but X, which is susceptibility. So what I will do is, before doing that, I'll take H to the other side. I'll have B by H over here. I'll have mu naught over here, and I'll have 1 plus I by H into mu naught. Now try to recollect what each one of them is, guys. Think about it, what each one of them is. B by H, try to recollect what was B by H. It was just mu, permeability, B by H. What is I by H? It was susceptibility. And that's it. It was, oh, I'm so sorry, guys. This mu naught was taken out common. I'm so sorry. So I'm just taking out mu naught as common. So mu naught is outside, my bad. And now I can take mu naught below. So this will become mu by mu naught is equal to 1 plus X. Now what is mu by mu naught? Mu by mu naught, remember permeability by permeability of free space, what is that quantity? That is nothing but relative permeability. So relative permeability is nothing but 1 plus X. That is the formula. That is the formula. I hope this is clear. Very, very important. Yes, that is the formula. I hope this is clear. I hope this is clear. So very important formulas, you should remember this. Relative permeability is 1 plus X. Okay? Yes, mu has been taken out, Science Priya. Yes, I took it out. All right. Now, think about it. Is it possible for a material to have permeability less than the permeability of vacuum? The answer is yes. Is it possible for a material to have permeability more than permeability of vacuum? The answer is yes. So the permeability of a material can be less than or more than that of vacuum. That's what we are going to see. Because of which this ratio that you see, relative permeability, it can be more than 1 or it can be less than 1. Okay, it can be more than 1 or it can be less than 1. Now, if it is more than 1, then understand X will be positive or susceptibility will be positive. But if this ratio is less than 1, then understand because it's less than 1, X will also be negative because it's 1 plus something. I should get something less than 1. So that's how it works. That's how it works. That's what we're going to see, Krito. Which material has permeability less than vacuum? That's what we're going to see. Don't worry about it. Okay, so let's start solving some questions. Let's start solving some questions. Very important questions. This will definitely clear all your concepts. Do not worry. Do not stop solving. No matter what, think, use your complete mind and see how to solve this. A wooden block is kept inside a long solenoid having n 100 turns per meter, through which current is 2 amperes. Find the magnetic intensity. X is given, susceptibility is given. Find intensity by which the block is also magnetized. So basically we have to find H and we have to also find I. Okay, so let's think about it. So I have kept a wooden block. Okay, so I have kept a wooden block inside a solenoid. Okay, and the current passing through it is 2 amperes. All right, and there are 100 turns per unit length per meter. Okay, so now think about it. The value of H, I just told you, is nothing but external field by mu naught. B naught is nothing but mu naught Ni. So mu naught goes, and I'll just be left with Ni. Now what is number of turns? Well, number of turns is 100, guys. And what is the current passing through it? The current passing through it is 2, correct? So 2 amperes and into 100, that is just going to give me 200. That's the answer. Check it out. And the unit, of course, is ampere per meter. So that's the answer for the first question. So this is the first answer. Now the next is find intensity of magnetization. I have to find out I feel I can find it out because X is given, susceptibility is given. Remember, just some time back I told you X is nothing but I divided by H. Therefore I will be nothing but XH. Now what is X? X is nothing but 2 into 10 to the power minus 6. Just check it out. Correct? So 2 into 10 to the power minus 6 into H. What is H? H is nothing but 200. So guys, 2 2s are 4, and that will become into 10 to the power minus 4. Again, ampere per meter. So that's the value of I. Now think about it and tell me, was this actually a difficult question if you know the formulas? Was it actually difficult? I don't really think so. So just stay with me. I'm going to make you practice many formulas and many problems now. So you will learn how to apply those formulas in the problem. So get ready now. All right. Very good. Very good. Many of you have understood this. Excellent, guys. Very good. Very good. Chalo, next question coming up on your screen now. An object has relative permeability as 0.5. Find the permeability and susceptibility. Also find the intensity of magnetization if magnetic intensity is 10 ampere per meter. So let's see what and all is given. Mu r is given, guys. So let's write down what and all is given for us. So mu r is nothing but 0.5. That's given. You have to find X, you have to find permeability, you have to find intensity of magnetization, provided magnetic intensity is 10. So H is given as 10 ampere per meter. So this is what is given to us. So guys, think about it. What is the first thing that we can find? I feel mu r is given. So I think I can find out mu, just the permeability. How? Remember, mu r is mu by mu naught. Therefore, mu is mu r into mu naught. Mu r is 0.5, correct? And mu naught, think about it, guys. I have told you about this, that mu naught divided by 4 pi is nothing but 10 to the power minus 7. Use that fact and put it over here. So mu naught will be nothing but 4 pi into 10 to the power minus 7. So this will become 4 into half is 2. So 2 pi into 10 to the power minus 7. That's the value of mu. That's the first answer that we got. I'm blocking this. So that is mu, guys. Okay. Next, we have got this. Okay. I hope this is clear. Next, let's find out susceptibility. I think I just gave you the formula. Mu r is nothing but 1 plus susceptibility. Mu r is already known. It is nothing but 0.5. So obviously I can find the susceptibility. The susceptibility will be nothing but negative 0.5, guys. Check it out. Check it out. The susceptibility will be negative 0.5. I hope this is clear. Okay, very good, very good. I hope you guys are understanding this. Follow me carefully, you will get it. Okay, next. What is the intensity of magnetization? Guys, we just have studied one formula. X is nothing but I by H. All right. And do I know H? Yes. So I can definitely find I. So I will be XH. Therefore, I will be nothing but X value is minus 0.5. Okay, minus 0.5 into 10. That's the value of H. So guys, that will be minus 5 ampere per meter. Now, if the value of I is negative, what does it mean? If the value of I is negative, what does it mean, guys? It just means that if the external field is towards here, the intensity of magnetization or the induced field is in the opposite direction. So it's not in the same direction. So all those materials whose induced field is opposite to the external field will have relative permeability less than 1 and susceptibility as negative. All those things whose I is in the same direction of external field will have relative permeability more than 1 and susceptibility as positive. Very important. I hope this makes sense. I hope this makes sense. All right. Shall we go ahead then? Okay. So I hope you are now getting to know how these terms play around. Let's get going to the next question. Very interesting question. There is an external field of 4 Tesla and it induces a parallel magnetic field of 1 Tesla inside a material. What is the net field inside? What is the magnetic intensity of the field and intensity of magnetization? Also find X. Everything we have to find, guys. Come on, let's get going. Let's start with the basic stuff. So what and all is given to us? Let's write down. External field B0 is given as 4 Tesla. Then induced magnetic field, it is parallel, so that means that B induced will be 1 Tesla. Okay, so immediately I can find out the net magnetic field, which is B0 plus B induced, and since they are in the same direction, 4 plus 1, that will give me 5 Tesla. So great, I have figured it out that the magnetic field is going to be 5 Tesla. Acha. Then what is the net field is done? What is the magnetic intensity? So find out the magnetic intensity. Okay, so what do we do? Acha, H is nothing but B0 by mu naught, guys. Is B0 known to us? Yes, B0 is 4. So 4 divided by, what is the value of mu naught? I just told you. It is nothing but 4 pi into 10 to the power minus 7. So 4 goes and you will have 10 to the power 7 divided by pi ampere per meter. That's the value of H. Very easy, guys. I hope you are understanding that these problems are not difficult when you know the formulas. So H is also done. Okay. Intensity of magnetization. Intensity of magnetization means I. So I will be B induced by mu naught. What is B induced? 1. Okay. What is mu naught? 4 pi into 10 to the power minus 7. So this will become 10 to the power 7 divided by 4 pi ampere per meter. So that's the value of I. That's also taken care of. Are you seeing, guys, with me? You are able to learn so many things. Lastly, we have to find out X. How do we find out X? That's also simple. Remember, X is I by H. X was I by H. So this divided by this. Just divide these two, guys. 10 to the power 7, 10 to the power 7 gone. Pi gone. So you will just have 1 divided by 4. So that's the value of X. That's also taken care of. Thank you, Pranav. Even I am from there originally, long time back. All right, Priyanka. All right, Yalni, Kirito. Very good. Kushbu, VK. Excelente. Yes. I hope you guys are now getting confidence. Are you getting confidence, guys? Let me know in the chat box. Are you feeling now a little bit comfortable with this topic? Shreya, the KVPI session will be next week. Yes, I have planned 2 KVPI sessions. One specially for SA, one specially for SX. Very good, Alika. Very good, Aishwarya. Very good, Mohammad. Very good. Very good. Very good. Yes. Let's get going to the next part now, where I'm going to tell you about diamagnetic, paramagnetic, ferromagnetic materials and their properties and then we are going to solve problems on that, and then we are also going to see bar magnets and their properties. Lot of stuff. I hope you guys have come prepared with your energy drinks. So let me also drink a little bit. Kirito, it will be given to you. If it is given as parallel, that means it is same direction. If it is anti-parallel, then it is opposite direction. Same here, Pranav, same here. The feelings are mutual. Now, for all the 12th standard students and the dropper students, I hope you have already checked out the special message from our co-founder, AP Sir, and he has mentioned about the Ekalavya program. So please go ahead and check out that video in case you haven't, because all your doubts will be answered there. This is a special batch for all the dropper and the 12th standard students, where you are going to get not just amazing master teachers and lot of test series guys, but you're also going to get a lot of assignments, questions, discussions, plus full syllabus and part syllabus test series, and special sessions by AP Sir, Pulkit Sir. And obviously after the advanced examination, you are going to have mentoring sessions for choosing a branch or choosing your college. These are the ranks which I have produced using for all those students who have been enrolled in Ekalavya last year, in fact. And you can see guys, the change that was created. Their mains rank, let's say for Chirag, was 731 before joining Ekalavya. After joining the Ekalavya program, his rank in advance is All India rank 41. It's not a joke. Look at the ranks. All India rank 1 in PWD category, and then for Dhruv it was 158 in mains and it became 43 in advance. So guys, check out the delta. Look at all the changes that have happened in all these students before and after. These sessions are free of cost and every detail about it is transparent. We have kept all the details on our website as well as the PDF link below. So all those students who are preparing for 2021 JEE Advanced, that is this year JEE Advanced, it's for them. So it's a special program and the only entry points are these. January 3rd Sunday, that is exactly tomorrow, there is a test. I hope you are preparing for it. So, and the next test is on January 7th and the next test is January 10th. Any of these tests you can write, understand, you can even give it multiple times if you want to, all right. And remember, you have to fill the form given in the link below over there. So forms.gle, just use this link and fill up all your details and give these tests. These are the only ways by which you can actually enter inside the Ekalavya program. I'll be teaching, Shimon sir and so many other teachers are teaching over there. So do not forget guys, this is very important if you want to prepare. And this program will also be there for NEET students, and this program will also be there for the next year students next year. So those of you are going to write in 2022, don't worry, we are going to again come up with the same program next year as well. So don't worry. Okay. So, wow, VK channel is drinking tender coconut. Kya baat hai? So Priyanka, exactly which class timing? Usually I conduct all my classes at 7 o'clock on YouTube. Otherwise, I conduct all my classes on the paid platform on Vedantu Pro subscription. All right. And what is this blue Muhammad? I'm not sure what exactly. Oh, it's not a blue drink. The glass color is blue, Muhammad. All right. Okay. Thank you, Elakya. All right. Very good. Even Krito is also drinking coconut milk. Wow, very good. Even I like, yeah. I especially like the tender coconut with that very thin layer. How many of you love that thin layer of that coconut? How many of you like that? All right. So you can tell me. Oh, Elakya likes it. I'm pretty sure Mohammed also likes it. Okay, Khushbu also likes it. Wow, Ankit, you are 22 army. Ankit, when are you going to become Enthuse army? Huh? Come on. Become a minion. Yes. Okay. So interesting. And guys, how many of you love coffee or tea? I just wanted to conduct a poll. Do you guys like coffee or do you guys like tea? Coffee or tea? I just wanted to know. Come on, exciting poll. Let's see. Tea or coffee? Those of you who love tea, put tea. Those of you like coffee, put a coffee out there. Okay. Khushbu likes party, looks like. Okay. tea, coffee. Arvind, I am right now in Bangalore. Okay, coffee, tea. Okay, both coffee. Looks like we have more coffee lovers though. All right, interesting. Even I like coffee, guys, but that's why I don't drink coffee, because if I start drinking coffee, then I'll become an addict. So that's why I drink tea. That's how it is. Okay, interesting. Oh, Khushbu, my New Year party was very good. And yeah, we just had a good time with my family. That's all. And all the other cousins and all. Wow. Yes, I have visited Ooty, and in fact, I have visited so many other places which produce tea and had their specially made tea powder and coffee powder and stuff. So it's very nice. Tanmay loves Boost. Oh, very different, Tanmay. Very good. Okay, so let's get going, guys, to the next thing. And this is going to be very interesting because Pandu and Champa are going to come back. So get ready to see Pandu and Champa. Get ready. So let's create an analogy for you guys to understand stuff very easily. Understand, any electron going around an atom, or even the electron itself when it spins, because they are charged particles, they behave like current carrying wires. Because when electrons flow, that's current. Charged particles move, that's current. So when they spin, when they move around the orbit, understand they are nothing but currents. And what do currents create? They produce magnetic field. Now, when a current like that is produced because of moving charged particles, it behaves like a small magnet, and that magnet will also have its own magnetic moment. That is, its north pole and south pole will be oriented in particular way, in particular direction. So the direction in which the magnetic moment is produced will now be thought of as like this. This minion out here, this Pandu out here, we are going to think as if he is that rotating electron, and the direction in which he looks is the direction of the magnetic moment. So just think about it this way. So he is like a small magnet, that electron which revolves, and the direction in which he looks is also the direction of the small magnetic moment produced by that electron. I hope everybody has understood till here. I hope everybody has understood till here. All right. Now, next thing. Let's assume some other electron is there. Let's say Champa comes out there, and the direction in which she looks will be the direction of the magnetic moment produced by that particular electron. Okay, so that's the magnetic moment produced by that particular electron. Okay, now in an atom there will be so many electrons. Each electron will have its own direction of magnetic moment. So in that complete atom, when there are so many electrons, can you think the total magnetic moment inside that atom will be the vector sum of all these magnetic moments? So when, example, both these electrons, both these QDs out there are there in the same atom, each one of them looking in different directions, their resultant magnetic moment will be given by the vector sum of all the individual magnetic moments. Is that clear? Is that clear, everyone? Very good. Okay. Deepak, please don't spam. And Pascal's law is very simple, so there is nothing to teach much about it, and I'll be conducting special problems on it. So please pay attention out here. Okay. Now, if you understood till here, then understand, when they are inside the same atom, their resultant can produce some net magnetic moment, or maybe if they look in opposite directions, maybe it can cancel out each other, and you will see that the net magnetic moment will be zero. So there are two possibilities inside an atom. The electrons' magnetic moments add up to give the resultant magnetic moment, or they perfectly cancel out each other and you will get net magnetic moment as zero. So atom as a whole, can I say, is a small bar magnet because of the tiny mini bar magnets produced by those electrons, and that atom will be a bar magnet if the electrons' magnetic moment do not cancel out each other, and if they all cancel out each other, then you will see that the net magnetic moment will be zero. The net magnetic moment will be zero. I hope this is clear. I hope this is clear. Very, very important. So an atom itself can have magnetic moment, or an atom itself may not have magnetic moment because they cancel out each other. Very, very important. Okay. Now just imagine each atom, alright, it may or it may not have magnetic moment, and in an object, alright, there are so many atoms, trillions of atoms, millions, trillions, billions of atoms. There are multiple possibilities here. Possibility 1, each atom is probably, okay, not having any magnetic moment. Each atom has zero magnetic moment. So because each of them has zero magnetic moment, the object as a whole will behave non-magnetic in nature. Think about it. Because each atom itself does not have magnetic moment. Why it does not have? Because each electron's magnetic moment cancel out each other. So the total magnetic moment is zero. I hope this is clear. That is one possibility. Or second possibility, each atom has its own magnetic moment. Each atom itself has its own magnetic moment, but they are oriented in a very random manner, because of which they cancel out each other, and that's why the whole object behaves non-magnetic in nature. I hope this is clear. So guys, yes, a lot of magnets out there. So when I say, oh, this is not a magnet, there are two possibilities. What are the two possibilities, guys? One possibility, each atom itself is not magnetic. That's why the object is not magnetic. Number one. Number two, each atom is magnetic, but each orientation is random, so they cancel out each other, and that's why you are seeing that the net magnetic moment is zero. Very, very important. Clear? Excellent. Ankit, first you become a minion army. First you become a minion. All right, all right. Okay. Oh yes, Kirito, there are magnetic fields definitely coming around you. Yes, yes, there are magnetic fields definitely coming around you, but just that they cancel out each other, that's why you're not magnetic. That's all. All right, all right. Okay, so now imagine we have lot of atoms. Each atom has many electrons. Some electrons are having magnetic field this way, some other electrons having magnetic field this way. So you have lot of atoms, each atom having many electrons, each having their own magnetic moment. Now we want to see what is the influence on these atoms because of some other material around it, some other external field around it, some other magnetic field around it. So somebody else comes and we want to know, how do these electrons behave? What exactly happens to these electrons? We want to know that. Now I'll tell you guys, there are three possibilities. There are three possibilities. And I'll tell you what are those three possibilities. Just imagine guys, you are in a class. Okay, just imagine you are in a class and all these minions out here are situated here. Okay, they are forming pairs, they are sitting on a bench. Okay, now each Pandu Champa, alright, their magnetic moments are cancelling out each other. What is happening? One is looking here, another is looking there. What will happen to each pair? The resultant magnetic moment will be zero. Do you guys get it? Pandu is looking here, Champa is looking there. Net magnetic moment for each bench is zero. Correct? Now, the teacher comes in, external agent comes in. The moment the external agent comes in, what happens, guys? What happens, guys? You know, each of them slightly change their orientation. Yes. How? This is what happens. All those Pandus or Champas which were looking towards the teacher, they slightly look away. What happens? All those Pandus or Champas looking towards the teacher, probably they don't like him or what, I don't know, they are scared, so they look away. Alright, and the ones which were slightly looking away from the teacher, they further move away. That means everybody is trying to look behind. The teacher is there, but you know, the external agent is there, but they're trying to turn back. And they are going to create a magnetic moment in the exact reverse direction. So that's what is going to happen. And that is material number one. That is one kind of material. Okay, so keep this in mind. This example you should keep in mind. That is one kind of material. Second kind of material, I'll tell you. Second kind of material is Pandu and Champa are not exactly opposite. Okay, they are not opposite. They are almost facing the same way. Okay, if Pandu is looking here, Champa is also almost looking here. So the atom as a whole has a magnetic moment. Now in each bench, each Pandu Champa are looking, one is looking here, one pair is looking there, another pair is looking here, another pair is looking here. So as a whole, the entire class has some random direction, so it has zero net resultant because each pair is looking in different directions. So the resultant of that class is zero, correct? Now what happens? The class teacher comes in, the external agent comes in. So what happens to all these pairs? Instead of looking away, they are slightly different. They start looking towards the teacher. They start looking towards the teacher. All of them start looking towards the teacher. All these Pandus and Champas. Now the moment this external agent goes away, they again come back. They again start looking towards the random directions. As soon as that external agent goes away. As soon as it comes in, again it looks here. As soon as it goes back, that's it. They start looking in weird directions. As soon as it comes back in, again these people start looking towards the teacher. That's what is going to happen. Very interesting. That's second type of material. And Prajwal, why don't you comment? Instead of always spamming over here, please comment below. I will definitely help you. Please, let's not break the flow of the topic. Okay, Prajwal? Now, yes, it happens in every classroom. Now the third kind is where there will be groups formed, and that is the third type. There will be groups formed. A group of Pandus and Champas will form a group. They'll be like, hey, you know what? We are going to look here. And there will be 10 pairs in that group. We are all going to look here. There will be another group, maybe the blue house, maybe the green house, maybe the yellow house, maybe the violet house, maybe the orange house. Orange house will say, hey, you know what? We are going to look over there. The yellow house will be like, hey, you know what? We are going to look there. Some other group will say, we are going to look there. As a whole, there is no unity. As a whole, the net magnetic field is zero. And we will see what happens when external agent comes in that situation as well. Yes, it is domains. Exactly. Exactly. So, yes. Oh, some people have already forgotten that houses existed. Thanks to lockdown, guys. Yes. All right. Okay. So, Prajwal, just because you come by the name of Pankaj, understand, I still know, please don't spam. Just put it up as a comment. After the video, I'll definitely help you out, bacha. Don't worry. Just put it up as a comment. Okay? Let's not break the flow. So now, let's see all these situations. First type of material. Come on, guys. I'm pretty sure you're going to love this and you're never going to forget this chapter, and you'll always remember this examples and you'll always score well. That's my promise. Okay. Now, the first type. Each atom itself has no magnetic moment. Look at them, guys. 0, 0, 0, 0, 0. Now, external effect comes. External field comes. This is where the teacher is. This is where the teacher is, guys. So that's why this is B0. This is the external field. The teacher is asking, hey, look towards me. Look towards me. So what are these atoms going to do? They're like, hey, I'm not going to look towards you. I'm going to look opposite. Look at that. North pole is here, South pole is there. North pole is here, South pole is there. That was the first type of material. Exactly opposite, guys. Do you see that? Do you see that? Do you see that? Everybody saw this? Very, very interesting. And guess what? The moment that external agent goes away, that's it, B0 has gone. These atoms lose their magnetic properties and come back to original. They were all looking behind. As soon as the teacher goes away, they will again come back to original, and net magnetic moment per bench or per atom is 0. That's what you should think. I hope this is clear. This is okay. Okay, fine, Pankaj, just hold on. Okay, fine, Pankaj, hold on. I'll answer all your doubts after the class. Please post it as a comment, okay? Now, this kind of material is called as a diamagnetic material. So, understand, guys, the magnetic field is produced in the exactly opposite direction. That is called as a diamagnetic material. I hope this is very clear. So, which kind of molecules or atoms behave this way. So let me give you examples. Diamagnetic material. Examples will be H2O, then you also have H2, then you also have NaCl, that's salt, then you also have silver, mercury, and diamond. All these are, even in fact you are a diamagnetic material, by the way. This is basically, yes Princey, I know that you have watched a part of this, but believe me, today there is something extra, because I'm going to also talk about bar magnets and stuff like that. Okay, so hold on, don't worry. I know some of you have already seen some parts in other biotonic, don't worry. Okay, and these material get repelled by the field. So very important, they are repelled by external field. You know what guys, there are videos on this. Yes, there are videos on this. They take a frog or an ant or stuff like that, small animal, and they produce a magnetic field from below. And guess what? Frogs, humans, etc. are diamagnetic in nature. So you know what will happen? We will be repelled by that field, so we will start floating. Now human body has a lot of mass and weight, so it's very difficult to make yourself float using an external field, but small animals like frog or insects like that, they can easily float using this principle of magnetic levitation. Very interesting it is. So very important property. Another thing, atoms don't have magnetic, very important, atoms don't have magnetic moment. Understand that. Okay, very important. And this is a temporary phenomena. That means as soon as the external field goes, the induced field will also go away. Very important. And the induced field which is there is going to be much lesser than external field. It's very small, it's not so strong. And remember, these both are opposite. These both are opposite in nature. Okay, if B naught is here, B induced is there. That's very important. And the last thing, because they are opposite, remember I told you about relative permeability and susceptibility. We just did a problem on that. Susceptibility is negative and relative permeability is less than 1. So those people who are asking, sir, whose relative permeability is less than 1? These are the materials which behave in this manner. I hope this is clear. I hope this is clear. All right, I hope you have also made notes for this. Okay, great. Let's go ahead to the next type of material. The next type, oh, by the way, before that, let me also tell you how the graph looks like. This is B versus H curve. B versus H curve. H is your input, how you are trying to magnetize it. B is what is being created inside that. This is the induced magnetic field which will be created inside it. So understand, if you try to magnetize it with some positive values, it's a diamagnetic material, so it will be exactly opposite. So it will be here. Arrow mark is like this. That means if you try to magnetize it with some positive values, the induced field is exactly opposite to that. And if you remove it, it will again come back to 0. So that's why the double arrow mark. Understand it. And if you try to magnetize it with negative values, again it will be induced in the positive direction, and when you remove it, again it will come back to 0. Okay, so that's the graph. Okay, that's the graph, guys. Very important, B versus H curve. And another important graph is that, you know, oops, 1 second. Yeah, how does the susceptibility change with temperature? For these materials, very important, it's a constant, very important. So with temperature, the susceptibility, the behavior of these materials do not change, it's a constant behavior. So it's independent of temperature. Very important. No problem. Nameless guy, I don't have your name out there. Okay. Next, we are going to talk about the next type of material. In this kind of material, you know, each atom has its magnetic moment. They do not have zero magnetic moment. Each of them has, but they are oriented in random directions. Now because they are oriented in random directions, the resultant magnetic field is zero. So the resultant is zero. At the moment there is an external field, these bar magnets are going to turn, but not opposite, but in fact in the direction. You will see that they are going to turn in the direction of the magnetic field. So they are little bit obedient students. They are not those kaminas who turned back. So they are going to turn in the direction of the teacher out there. So you will see these magnetic fields are going to assist. Yes, they are going to help the external field. So inside the magnetic field will be much stronger. And in fact, it will be attracted. It will be attracted by the external field. What happens when the external field goes away? When the external field is removed, okay, so when it goes away, even these magnets return back to their original random orientations. So again, it's a temporary phenomena, like you can see. Okay, yes, Mrinmay, I do take. Now, let's talk about what this material is called. This is called as a paramagnetic material. Remember, this is called as a paramagnetic material. So what are the examples of paramagnetic material? 1 second, guys. Yes. Yeah, the examples of paramagnetic material are aluminium, manganese, magnesium. All right. So all these are examples. Then sodium, then potassium, then oxygen. Again, this is a temporary phenomena. Very important. Here, atoms have magnetic moment. So there is a magnetic moment for the atom and it is not zero. Okay. And again, the next thing, the induced magnetic field is very less. It's not so large, guys, as compared to the external field. And these both are in the same direction. Very important. Now because they are in the same direction, you will see that the relative permeability will be more than 1. Okay, it will be more than 1. But the susceptibility will be a small positive number. It's not going to be very huge because the induced field is not very large. Very, very important. Okay, so I hope this is clear. Yes. Okay. Rajesh, happy new year to you too. Okay, chalo, let's get going to the next part. And how will the BH curve look like? The BH curve, if you try to magnetize it in the positive way, then the magnetic field induced will be also in the same direction. If you remove it, it will come back. And if you try to magnetize it in the reverse direction, induced field will be also in the reverse direction. And if you remove it, again it will go back to the same point. So this is also very, very important. I hope this is clear. Okay. And how does it behave with effect to temperature? So if you increase the temperature, X reduces. Susceptibility is inversely proportional to temperature. In fact, this is also called as Curie's law. Remember this, they can give you these kind of questions. Very simple. How does the graph look like? If this is the temperature, this is the susceptibility. What is the susceptibility at this temperature for a paramagnetic material? Rohan, these are JEE lectures. I'm not sure for IPO. But you know, obviously this will lay the foundation. But for IPO, there will be obviously higher level problems which will be needed. Okay, great. Yes, this is a rectangular hyperbola as well. And this is how the graph looks like. As you increase the temperature, the susceptibility reduces. Remember that. So Rohan, this will only lay the foundation, but for problems you need to attend special batches. Okay, great. Now let's talk about that groupism that was being formed, guys. Remember that groupism? So each group is called as a domain. What is each group called as? It is called as a domain. And each group will look in a particular direction. So they will have their own magnetic moment. Why it happens, etc., that is not there in our syllabus. Just let's assume that a group of bunch of atoms, molecules always tend to look in one particular direction. That's how their property is. Now in a object there will be many such domains. Domain 1, domain 2, 3, 4, 5, 6, 100, 200, thousands of domains might be there. Each one will be oriented in different directions. So the object as a whole has zero magnetic moment. The object as a whole has zero magnetic moment. Now, when, oh, by the way, this is how the domains look like, okay, in the object. So they are oriented. These arrow marks point in the direction of magnetic moment. So you can see it's randomly oriented. Now, what happens when you have an external agent coming in? So before that external agent came in, these domains were randomly arranged. The moment an external agent comes, guess what happens? All those domains which are pointing in this direction towards him will start increasing in size. They will accumulate more and more people. It's like, you know, all the groups which were looking towards the teacher, they catch hold of other people, like, hey, come on, join in my group. Hey, come on, join in my group. And they expand, guys. So they have more and more domains pointing towards the same direction. And that's how it gets magnetized in the direction of the external field. The moment this external agent, so this is how the orientations look like, they almost try to align themselves. They try to align themselves in the direction of external field. The moment the external field goes away, so what will happen is they will still retain their property. Yes, understand this was before. After the external field goes away, the groups do not change. All those people who were conquered, they stay there and it retains its property. That means it's not a temporary phenomena. It has been permanently magnetized. So that's why these materials can be used to make bar magnets, horseshoe magnets and stuff like that. I hope this is clear. Yes. No, this is not a hypothetical phenomena. These are real phenomena. It's just that I'm giving you simple examples so that you understand all these things. Okay. So this is how the domains look before magnetization. This is how the domains look after magnetization. And even when you remove the external field, they try to maintain their orientations. That's why it's a permanent magnet and they are called as ferromagnetic materials. Very, very important. They are called as ferromagnetic materials. So which are the examples of ferromagnetic materials, guys? So obviously ferrous or iron, okay, cobalt, then nickel. All these are examples. Obviously they are permanent in nature. So the effect is permanent, okay. And this is because of domain formation, not because of atoms or anything. So because of domains, and the induced field is much higher than the external field, okay, and they are in the same direction, guys, okay, they are in the same direction. So the susceptibility will be much more than, much more than 0 in fact, and the relative permeability will also be much higher than 1. So this is how these values play out to be. Very, very important. Very good. Very good. I hope you guys have understood this. Okay. After this, let me know, guys, will you ever forget all these things? I'm pretty sure you can't. And how does it behave with temperature? So the graph of susceptibility with temperature is something like this. Okay. So this is the graph. It is like this. Okay, and basically it's almost a constant, guys, till a particular temperature called as Curie's temperature. Till a particular temperature, the graph is almost constant, susceptibility versus temperature. That means it does not get affected by temperature. The moment the temperature crosses the Curie's temperature, it becomes like a rectangular hyperbola, just like paramagnetic materials. So the susceptibility is again basically some constant by T minus Tc. So basically this is valid only when temperature is more than Tc. Curie's temperature. So till that Curie's temperature, till you heat it till Curie's temperature, nothing happens. Only when you cross that Curie's temperature, the susceptibility behaves like a paramagnetic material. Yes. Okay. Great. Okay. So let's solve some questions. And before that, the BH curve. This is also very, very important, guys. This is also very, very important. So what happens is, if you try to magnetize it, the induced field will also increase drastically. If you try to create some magnetic field from outside, the induced field will also increase. But the moment you remove the external field, it will not come back to 0. It will almost come back till the same value. It will almost come back to the same value. But it might be slightly less, but there is some magnetic field which is still induced. Look at that. The graph's arrow marks are very important. The arrow mark is not via the same path. So when you increase the external field, the induced magnetic field increases, but when you remove it, it retains it, because you know the domains are still almost arranged in the same direction. This much is called as retentivity, or how much is remaining. How much is remaining even when you remove the external field. That's what it means. And because the path of going and path of coming back is not the same, that's why it is called as the hysteresis. So hysteresis is basically whenever the path of going and path of coming, it's like a one way. You can go via this way, but you can't come via same path. You have to come via a different route. So that is called as hysteresis. Very important. Similarly, when you now, if you take that same material and create or you apply external field in the opposite direction, then you have to apply some amount of external field to make it zero, the induced field zero. That much is called as coercivity. That much is called as coercivity. So coercivity is basically how much negative external magnetizing field you need so that the induced field becomes zero. So it basically loses all its magnetic properties. So earlier all the domains were pointing in one particular way, so you create ulta, you create opposite magnetic field so that the domains get destroyed and they are again oriented back in random directions. That's coercivity. So I hope you have understood the BH curve out here. Yes. Okay. So let's see the first question. Under the influence of same uniform field, the net field for three materials is as shown. Which one is dia, which one is para, which one is ferro? Look at these. Which one do you think is dia, para and ferro? Come on, think about it. Let me know. I feel this one is the dia, guys, because look at the field. They're trying to go away. It does not like it. The field lines are going away from this material. Now if you look at these, the field lines which are coming from outside are coming inside the material, but if you compare both of them, here there is a more tendency of being attracted. So the field lines are stronger here as compared to this. So this must be para and this must be ferro. So that's how it is. In dia they repel, in ferro and para they attract, but in ferro the attraction is even stronger. So that's how you compare them. Okay, got it guys? Very good. Chalo. Alright, next question coming up on your screen. Which of the following has positive relative permeability but negative susceptibility? Come on, if you have been paying attention closely, then you already know the answer. Which of the following has positive relative permeability but negative susceptibility? Come on guys, come on. Positive relative permeability, guys. Alright, a lot of you are saying B. Okay. Guys, I think you guys have forgotten. The answer is A, diamagnetic, guys. I just told you. I think you just forgot. For diamagnetic, susceptibility is negative. See guys, I'll tell you. After this you will not forget. Okay. So this is for dia, this is for para, this is for ferro. Okay. And you have X over here, you have relative permeability over here. Okay. So guys, let me tell you, you will not forget now. For dia, it is negative. For para, it is positive. For ferro, it is extremely positive. Mu r for dia is positive but less than 1. So somewhere between 0 and 1. For para, it is more than 1. Okay, something more than 1. So 1, say something plus. Okay. But for ferro, obviously it is more than 1, but really large. Like 100, 1000, 2000, like that. So that's the difference. Okay? I hope this is clear. I hope now you will not forget this. Remember this chart. Very important. Is that correct, guys? Everybody understood? Shall we go ahead to the next question? Shall we go ahead to the next question? Come on, let me know. Quickly in the chat box. Go ahead. And if you want to drink a juice or grab a sandwich, go ahead and have it as well. Next question coming up on your screen. Next question, and here it is. About dash temperature, a ferromagnetic material becomes dash magnetic. What happens to it? About dash temperature, a ferromagnetic becomes dash magnetic. Come on. Both the blanks you have to fill, guys. Come on, both the blanks. Yes, all right, come on. Filling the blanks. Yes. Not critical, it is called as Curie's temperature. Above Curie's temperature, a ferromagnetic material behaves like a paramagnetic material. Guys, this is a graph for a paramagnetic material. Remember that? This is how the graph is for a paramagnetic material. But for a ferromagnetic material, till Curie's temperature, doesn't matter. It's ferromagnetic. About Curie's temperature, the graph is like this. I just gave you that graph. So that is basically paramagnetic nature. So that's how it behaves. The ferromagnetic domains are broken and it becomes paramagnetic. Very important. Now, are you guys ready for the next part, which is bar magnets, dipoles, magnetic moment and their problems? A lot of problems coming up. More 30-40 minutes and then we are done. All right. So guys, grab a sandwich or something. Come on. Okay. So I hope this is clear. Rahul, I'm not sure which standard are you in, and have you undergone any kind of coaching or stuff like that till now? And just don't worry, watch the lecture again after some time. Watch it 2-3 times. Do not give up, but that's very important. So if you're in class 12th, then definitely you should understand it, because there are some class 10th students also over here who are understanding it. So I know different people have different speeds. So don't worry, watch the replay, because all the lectures get saved. Okay, great. Okay, very good. Krito will finish a coconut milk. All right, interesting. So get ready, guys. Oh, Science Priya, mom did not give you the sandwich. Oh, so sad, yeah. Oh, by the way, guess, guys, what am I going to have after this marathon session? Any guesses what am I going to have? And that's why I'm not eating anything now during the marathon session, deliberately, because I want to keep my stomach empty, because I want to grab it after the lecture. Guess what? Oh my god, Frederick is also from 9th. Oh no, Ankit, for samosas I won't keep my stomach empty. No, pizza. Yes, it's my favorite, but in fact, no, not the pizza. Don't worry, Rahul, you're not dull. Why are you crying? You're not dull at all. Nobody is dull, nobody is intelligent, Rahul. It's just that you need some confidence. Don't worry, beta. You'll understand it. See, some people need 2 explanations, some people need 1 explanation. It's okay, na? Happens. Just revise it 2-3 times, beta. You'll understand. And if you still have doubts, ask your class teachers in the pro subscription, etc. Or you can also take help from all the other students here. They will help you out. We are all minion community. Don't worry, beta. Okay? No, not paneer naan. No, full meals, pasta, no. Well, actually, I'm going to have pav bhaji, guys. One of my favorite foods. And how many of you love pav bhaji? Let me know in the chat section out there. Yes, please let me know. Okay. Yes, Karthik, I'm going to come up with sprints, PYQs. Guys, you know what is the best part? 2021 is very lucky and time is with us. You know why? Because exams have been postponed. You have more time for preparation for boards. That means, guys, do we need to hurry up with the syllabus by taking one shots right now? Should we do everything in one lecture? Should we hurry up everything and skip all the details? Or do you still want to continue with the same pace? Let me know in the comment box, let me know in the chat box, and show some love. Yes, A lot of you like pav bhaji. Wow, very good. Yes, I like khichdi, but not so much. I feel that I use it. I have it whenever I'm sick, not otherwise. Okay. How many days to spend on a chapter? As long as you are confident, Shreyas. As long as you are confident. Okay. Karthik, you will get prepared. Don't worry. You are here. You are here in We Enthuse, and we are going to be there with you till the end for all the 11th, 12th, 10th, dropper, all kinds of students we are going to launch, and we are continuing with all the series. We are going to complete all the syllabus out here. We are going to have previous year question papers. We are going to have Menti quizzes. We are also giving you so many problems to practice. How much more, guys? Trust, have some faith, have some patience. Everything will be done. Yes, Sankit definitely will come up. We are going to definitely come up with 2022 series as well next year. Obviously, we are going to have 2023 series also next year. Next academic year, as soon as the batch ends. Don't worry about it. Everything has been planned. No, Princey, I don't. Yes, Shankar, I know a lot of portions have been completed here. Don't worry. If you have backlogs, take your time. You will reach here. A lot of students out here have started late even on this channel. But they had patience, they had faith, and they have reached the live classes. They have overcome their backlogs. You will also do it. Don't worry. Yes. So ready? So guys, if you still have more doubts, and if you want more test series and assignments, and you want to learn under me and many teachers like me under many micro courses, so pro subscription is for you. Go check out all the details for 2021, for 2022, and also the dropper students. All the prices have been mentioned in the description box below, and there is a 20% offer running right now, and you can use the discount coupon SHHPRO. Using the discount coupon, you are going to get 20% off flat. Please read all the FAQs. Please read everything in detail before joining in. And if you feel that you want to join only for 1 month, that's okay. That's completely understandable. Just join for 1 month, and if you feel like continuing, go ahead with it. All right. So let's continue with our session, and let's talk about bar magnets, guys. Oh, by the way, I just received a beautiful plate of French fries, and these are cheese balls. Okay, I'm just going to grab one of that just before the pav bhaji. These are some starters. All right. Pankaj, I'm not that usual teacher, who will always talk serious stuff. Understand, you need to have these conversations so that the bond is built. Don't worry, I'm not wasting your time. All right. So, if you want your doubts to be cleared, obviously you can put it up in the comment box, or you can definitely ask the class teachers in the pro subscription. Don't worry, I'm not wasting anybody's time. You need to form the bond. If we are so formal, then how will the bond build up, beta? Hai na, Pankaj? Understand that. All right. Chalo. Now let's talk about bar magnets. Now, I have already told you that the field lines originate from the north, appear to terminate at the south, and continue inside the magnet. The field is very strong here and becomes weak on the sides or far away from it. There are two poles in that magnet, but actually speaking, are there two poles inside the magnet? The answer is no, because even if you try to break a magnet into two parts, you will get two small bar magnets, each having north-south, north-south. If you break that bar magnet, there will be again a smaller magnet, north-south, north-south. In fact, you can never separate. Yes, you can never separate the poles of a magnet, strictly speaking. So then what exactly is the meaning of north pole and south pole? I'll come to it. I hope now you can relate this to electric dipole. Now, what is the meaning of a magnetic dipole? So, here is the thing. Understand that in a bar magnet, there is nothing like a north pole or a south pole, because if I break it, I will again get a south and a north here. If I break this, again I'll get a south and a north here. no matter how small I break it into, I will always have north, south, north, south, north, south magnets out there. Now, the meaning of North Pole and South Pole in a magnet is that, try to recollect, you know, electric dipole. Do you remember electric dipole? Positive and negative charge. How do the field lines look like? The field lines look something like this. The field lines look something like this. I hope you remember. Correct? Now, just imagine I happen to place an electric dipole over here. Negative charge here, positive charge here, and this is the electric field lines. Where should I place the negative charge and positive charge so that the electric field lines look very much similar to the magnetic field lines? Where should I place the electric charges so that you know, the magnetic field lines look exactly similar to the electric field lines? That's where the magnetic poles are. I hope this is clear. No, not at the midpoint. So the magnetic poles are roughly a hypothetical concept where you can replace it with electric charges so that the magnetic field lines look very much identical to it. Yes, correct. That's very important for you guys to understand. Then you'll be like, sir, where are these poles? Are they located at the ends? The answer is no. In fact, if the length of the magnet, this is called as the geometric length. This is called as the geometric length of the magnet. It has been found by drawing various field lines, diagrams, and putting iron fillings and stuff like that and comparing. It's found that the distance between the magnetic poles, which I call it now the magnetic length, this magnetic length is approximately 5 by 6 times, it's slightly inside, times the geometric length. This is 5 by 6 times the geometric length. Very, very important. I hope this is clear. I hope this is clear. Is that understood, everyone? So this has been found experimentally. Very, very important. Great. So this is the magnetic length. This is a distance between the poles. Now these poles are not physically present. This is hypothetically assumed to be present so that they create the same field like the electric dipoles that we have. Very good. Now, what is the strength of a pole called? The strength, like you have charges, positive charge, negative charge, you have north pole, you have south pole. The pole strength is denoted by the symbol. Some books use the symbol QM, but in fact, I'm going to call it just as small m. That's the pole strength. This m can be positive. If it is positive, it is a north pole, and if it is negative, then it is a south pole. Understand that. It's the south pole. So these two poles depends how strong they are. That's mentioned by this pole strength. If m is large, the north pole is very strong. If south pole is strong, then this minus m is very strong. So pole strength decides how strong each pole is. So can it happen that in a magnet, one pole strength is 2m plus 2m, another is minus m? That's never going to happen. They always will be in equal amounts. They always will be in equal amounts. That's very, very important. So if this is plus 2m, this has to be minus 2m. Or if that one is minus 3m, then this has to be plus 3m. That's why it's called as a dipole. Remember that. Dipole means equal strength but opposite signs. Very, very important. I hope this is clear. Great. What will be the units? We'll come to that. Don't worry. Don't worry. Okay. So we have spoken about pole strength, magnetic length, how it's related to the geometric length. Now the two poles together form a dipole, and they will also have a dipole moment. So the south pole is like minus m, and this is nothing but plus m, and the distance from one pole to other, if I call it as L, this L is nothing but magnetic length. Be careful, it's not geometric length. Magnetic length Usually in the problems they give you magnetic length unless specified otherwise. Remember it. Unless specified otherwise, it's always the magnetic length. Remember, electric dipole moment was charge into length. That's how the formula was. So magnetic dipole moment will be magnetic charge into magnetic length. As simple as that. So this is nothing but magnetic dipole moment. This is nothing but magnetic charge, equivalent of charge in magnetism, and this is magnetic length. So now think about it. Magnetic dipole moment, we have studied this already. Formula for that was NIA, etc. Remember that? So guys, think about it. M will be having the unit of NIA, number of turns into current into area. Number of turns does not have any unit. Current has the unit of ampere and area has the unit of meter square. Magnetic strength or magnetic pole charge, I don't know what is the unit, so let's think about it. This is length. It has a dimensions of meters. So when it goes here, that meter will get cancelled and you'll just have ampere meter. That is the unit of this magnetic charge. Very, very important. Ampere meter. I hope this is clear. I hope this is clear. Okay. Understood? Very good. So guys, let's not deviate from the topic. Rahul, why don't you comment later on or just message me on Instagram? Yeah, I'll help you out. Whatever doubts you have. Okay? Okay. Yes, Ankit, I like besan ka laddu. Come on, focus. Now, if everything is clear till this point, understand what's the direction of this? What's the direction? This is also a vector quantity. The direction is just like electric dipole moment. It will be from negative to positive. So that's the direction of M vector. From minus to plus, remember it. Very, very important. Okay, excellent. Let's get going. Now, let's see if we can solve this problem. Read this problem. 3 identical bar magnets, each of magnetic moment M, are arranged in the form of an equilateral triangle. Draw it. Unless and until you draw it, you will not get it. Such that unlike poles are in contact, the resultant magnetic moment is, come on, think about it. Meanwhile, I'll have some cheese balls. Come on, think. Okay, very good. Looks like many of you have understood how to solve this. Guys, think about it. This is your equilateral triangle. 3 identical magnets, that means equilateral triangle, such that if this is the north pole of one magnet, it is with the south pole of the other magnet. This is north pole, this is south pole, this is north pole. Guys, think about their magnetic moments. One magnetic moment will be here, M. Another magnetic moment will be here. Another magnetic moment will be here. You add it like vectors, remember? Each one of them is a vector quantity. What will happen? It's forming a closed polygon. So what will be the resultant magnetic moment? It will be 0. That's it. That's it. So the answer is 0. I hope this is clear. Yes. 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 Guys, please talk in English, yeah? Come on. No, please don't talk in Tamil. Then others will be left out of the conversation. Come on, VK and others. All right. Very good, VK. Krito, Alka, Sandesh, Princey. Yes, very good. Now, let's go to the next concept and then we'll also have some problems. The answer was 0, like I just said. I hope you remember this diagram. We have done this in electric field also. If you have a dipole, what is the field due to a dipole at any point? We have done this. We have done this, guys, and try to recollect the answer. If this is a magnet and you are at a distance r and this is angle theta, the magnetic field at that point, I have already told you. What is the magnetic field at any point? Come on, try and recollect. Let's see how many of you remember this from electric field lecture. How many of you remember this? Come on, guys. It's very similar. Instead of 1 upon 4 pi epsilon naught, you will have mu naught by 4 pi. Instead of electric dipole moment, you will have magnetic dipole moment, guys. That's it. You'll have magnetic dipole moment, and you will also have r cube over here, and you will have, think about it, 3 cos square theta plus 1. That's it. That's the formula. And remember, this line is called as the actual position, and this line was called as the equatorial position. So for actual position, put theta as 0, and for equatorial position, put theta as 90 degrees. Now it can be even 180 degrees if you're on the other side. So if you're on the other side, it will be 180 degrees. That's how this works. I hope you can relate the two formulas. So if you study them together, you will never forget it, guys. You'll never forget it. That's the first thing, field due to a bar magnet. Very good. Sandesh will complete it soon, don't worry. Within a month or two. Okay, don't worry, we still have a lot of time. Okay. And we'll be also conducting meanwhile a lot of KVPR sessions, Menti quizzes, PYQs, marathons, so many other things. So that way we'll be simultaneously also revising. Okay, what about potential at any point? Similar formula, potential due to a bar magnet, guys. Instead of 1 upon 4 pi epsilon naught, you will have mu naught by 4 pi. Instead of P, you will have magnetic dipole moment. Instead of R cube, you will have R squared dimensionally, and you will just have cos theta over here. So guys, try to recollect. We have seen this. If you are anywhere on the equator where theta is 90 degrees, potential is 0. They're all equipotential points because you are equidistant from north and south pole. So the potentials due to north and south cancel out each other. Potential is a scalar quantity, remember that. So if you are on this side, it's positive. If you are on that side, it's negative. Remember that. So on the equator, everywhere the potential is 0. Okay. Okay. Very good. Very good. Very good. Very good. Chalo, let's get going to the next part. Again, revision, guys. What happens if you place a dipole in somebody else's magnetic field? What happens? There will be a torque on it, and there is a magnetic moment M. And if this angle is theta, what is the torque given by? Vector form is M cross B. Instead of P cross E in electricity, here it is M, magnetic dipole moment cross B, and magnitude wise it is MB sine theta. We have seen this before as well. Yes, you will have a torque, very simple. So if you have a bar magnet in somebody else's, maybe this is a Earth's magnetic field, maybe you have a magnetic needle, there will be a torque which will rotate the needle and align it in the Earth's magnetic field. By the way, I'm going to conduct a special lecture on Earth's magnetic field. Do you want it? If you want it, do not forget to hit the like button and also put it up in the comments. Okay, next, potential energy, guys. Same thing again. U will be equal to minus M vector dot B vector. And if this angle is theta, this is M, obviously this will be nothing but minus MB cos theta. And we also take, when theta is 90 degree, understand U will be equal to 0. So this is our reference. So with reference to 90 degrees, so when this bar magnet is perpendicular to the field, that's when we take U or potential energy as 0. Yes, very, very important. Okay. By the way, this topic is only there in JEE Mains. Do you know that? Not many people know this. This entire chapter is only there in JEE Mains. It's not there in JEE Advanced. So guys, it's very important that you know the syllabus also. Rajesh, I hope that clears it. Yes. Okay. Now, here is the first question. Let's solve these questions. These are few questions which are left, and then we are done with today's session. Come on. So it will shift it in the direction of external field. Understand that, not current. Come on, solve this question, guys. Come on, come on, come on, quickly, quickly, quickly. Let me have some fries as well. No, Rajesh, it's considered difficult because the terms are difficult and it's confusing. In mains, all these confusing elements are there. If you learn this, that's it, you're done. minus 5. Okay, let's have a look. A bar magnet of magnetic moment, that means M is 5. Magnetic field B is 2. Theta is 60 degrees. The potential energy is how much? Remember, I just told you minus MB cos theta. So what is M? M is 5. What is B? B is 2. What is cos 60? Cos 60 is nothing but half. So what will you get? Minus 5 joules. That's the answer. Look at it. How simple it is. So guys, this chapter, many people keep it as an option, thinking that it's very difficult, it's confusing. But trust me, you have seen it today. If you study it properly and if you study it the way I have told you, that's it. Nobody can stop you from scoring all the marks that you will probably can score in the examination. Whatever question comes in the examination, you will be able to get it. Don't worry. Next question. So answer is minus 5 joules. Next question coming up on your screen. There is a magnet which is parallel to the uniform magnetic field, and the work done in rotating the magnet through 60 degrees is 24 into 10 to the power minus 5 joules. The work done in rotating through another 60 degrees is, come on guys, you can do it. Quickly, post up the answers. It's not that difficult. If you have got the previous question, you will definitely get this question as well. Come on, think about the work. Earlier it was at 0 degrees, now it's moved to 60, then again it's moved by further 60 degrees. If initial work is 24 into 10 to the power minus 5 joules, what is the extra work you need to do? It's not that difficult. Very good, Dinesh. Let the Joshometer be on its full scale deflection on the Joshometer. Very good. So what you need to do is think about each angle and what is the potential energy. First time, the potential energy will be minus MB cos 0 when you are at 0 degrees. So it will be basically cos 0 is 1, so it will be minus MB. Then when you are at 60 degrees, what will be the potential energy? Minus MB cos 60. What is cos 60? It's half. So it will become minus MB by 2, guys. And when you further rotate it by 60, the angle will be 120 degrees. 120 degrees. So minus MB cos 120. What is cos 120? What is cos 120? Minus half. Minus minus becomes plus. So it will become plus MB by 2. Now think about it, guys. From 0 to 60, okay, the work done from 0 to 60, correct, will be change in the potential energy. So U60 minus U0. What is U60? It's minus MB by 2, correct? So it's minus MB by 2 minus the initial energy. What is it? It's minus MB. So what will be minus MB by 2 minus MB? It will be plus MB by 2. So plus MB by 2 is 24 into 10 to the power minus 5 joules. Correct? This was from 0 to 60 degrees. Now think about it, guys. What will be the work done from 60 to 120 degrees? It will be change in the potential energy. U120 minus U60. Change in the potential energy. So this minus this. So it will be MB by 2 minus MB by 2, which is nothing but just MB. Correct? MB by 2 minus MB by 2. Final minus initial. So if MB by 2 is 24 into 10 to the power minus 5, what will be just MB equal to? MB will be twice of 24, so it will become 48 into 10 to the power minus 5 joules. And that should be the final answer. I hope this is clear. It's not megabytes. Understand, M is magnetic dipole moment, B is magnetic field. So it's 48 into 10 to the power minus 5 joules. I hope this is clear. Understood, guys? Let me know. Excelente. Let's get going. 48 into 10 to the power minus 5. Next question coming up on your screens. The maximum torque acting on the magnet of length so and so meters in uniform field having this much external field 2 into 10 to the power minus 1 Tesla is 10 Newton meter. What is its pole strength? Very interesting question. Let's see how many of you can do this, because this is the last question for today. This is the last question for today. Come on, guys. Come on. Manish, you might just have at least one question on this. and one question is 4 marks, and 4 marks is 1000 to 2000 ranks depending on where your ranking is. So it will decide whether you're going to get a college or not going to get a college. Very good, very good. Okay, chalo, let's get this question now. So guys, the maximum torque. When do you think the torque is maximum? The torque is going to be maximum when theta is 90 degrees, because torque is mb sine theta. So whenever theta is 90, sine is 1, that's the maximum value. So now the torque is given to us. M is magnetic pole strength into L, correct? And B is as it is, sine 90 is 1. So that is 1. Great. What do we have to find is M. So M will be tau by BL. What is the torque? The torque is 10 Newton meter. What is the field? Field is 2 into 10 to the power minus 1 Tesla. What is the length? Length is 2 into 10 to the power minus 1 meters. So guys, think about it. What's going to happen? 10 by 2 into 2, 10 by 4. 10 by 4 is nothing but 2.5 guys. Okay, and into 10 to the power 1 into 10 to the power 1, which is going to make it 250. But this is pole strength. So pole strength has a unit ampere meter. That's the answer. That's the answer to this question. Very good. Excellent guys. I hope you guys got it. It's not that difficult. If you know the formulas, if you know the concept, you can definitely score full marks in this chapter. This will for sure guarantee you 4 marks. That's a boost of plus 1000 rank. It will decide whether you get inside an IIT or whether you are not going to get inside an IIT. Remember that. So all those people who are going to leave this chapter as an option, obviously consider yourself that your rank is going to reduce by at least 1000 to 2000 ranks for sure, guaranteed. If you do this chapter, plus 1000 ka boost already. So somebody has already asked you, when is the Ekalavya batch going to start? The Ekalavya batch, Shreya, is going to start very soon by January mid, all right, or January end. So don't worry, we're going to start it. Very good. So that's it for today, guys. And by the way, these are our stars: Ruchir, Yalni, Aishwarya, Ankit. Excellent. Very good. You have been posting answers in the comment section. So these are your homework questions for today. A bar magnet of magnetic moment so and so lies in the direction of field. What is the work done in turning the magnet opposite to the field, and what is the torque required to keep in that position? That's your first question. And second question is, an isolated unit, North Pole, experiences so and so force when kept at a distance of so and so meters from a magnetic pole in air. What is the pole strength of that pole? Very interesting question. So check it out. Post the answers in the comment box after the video ends. Do not forget to solve it. And guys, remember, the Ekalavya batch is free of cost. Some of you are saying it's paid. No, it's not paid. It's free of cost. And they are going to be amazing mentors. And you will have special sessions from AP Sir, Pulkit Sir, 15 plus full syllabus test series, 2000 questions in the surgical strike assignment, and obviously you will have lots of module discussions. Yes, they are not just assignments. We are going to also have discussions after these assignments and the modules that you will be given. And you will also have post-advanced mentoring. So as soon as your advanced results are out, so before you get into the college, the IIT counseling which is going to happen. So we are also going to counsel you for grabbing your seat in the IITs, NITs and BITS. Remember that. So remember, tomorrow is the first entrance, January 3rd, Sunday that is. The next entrance on Thursday, January 7th. And the next entrance next Sunday, that's January 10th. And please fill up the Google form. Without that, you will not be able to enter into this batch. Remember that. So Pahul, you should solve almost all the questions. You should solve the objective 1, objective 2, short answer questions, and at least 60 to 70% exercise questions. Okay. Yes, the enrollment has started, Saurabh. Yes, they have. Okay, so do check out our Telegram group for more details, and do not forget to hit the subscribe and do not forget to hit the like button out there, because without your likes, guys, you're not going to show us your support. All right. What an amazing session it was. Very good, minions. Take care. This was Shreyas, your anchor for this channel. Bye bye. Have a great night ahead. See you on Monday with a special session for KVPY. So we're going to start our next week with a KVPY session. Stay tuned and I'll meet you at 7 o'clock on Monday. Bye bye. Have a happy weekend.